Today the subject name is electronic devices and circuits. So in this you have the topics energy bands in intrinsic and extrinsic semiconductors, equilibrium carrier concentration, direct and indirect band gap semiconductors. In carrier transport, diffusion current, drift current, mobility and resistivity, generation and recombination of carriers, Poisson and continuity equations, PN junction, GINA diode, BJT, mass capacitor, MOSFET, LED, photodiode and solar cells. So the first topics energy bands in intrinsic and extrinsic semiconductors, equilibrium carrier concentration, direct and indirect band gap semiconductors. All these are come under the semiconductors, isn't it? So in this we know very well electronic engineering is about the study of charge carrier transportation, that is electrons and holes through vacuum tube, gases and semiconductors. So generally what is electronics? The branch of engineering which deals with the current conduction through a vacuum or gas or a semiconductor is known as electronics. Electronics essentially deals with the electronic devices and their utilization. An electronic device is that in which current flows through a vacuum or gas or a semiconductor. So first of all, we know very well, according to Bohr model, nucleus having protons and neutrons. Nucleus having protons and neutrons. In that, protons have positive charge, neutrons have no charge. So finally, what it get? So this is the nucleus. So nucleus consisting positive charge. So atom is consisting nucleus. Electrons are revolve around the nucleus. Electrons are revolve around the nucleus. So this nucleus having both protons and neutrons. So electrons revolve around the nucleus. So actually what happens? Protons has positive charge. So that's why we here give the plus. Okay, so one doubt we have to be create here. What is that? So actually electron have negative charge, proton have positive charge. So those two are opposite charges attracted to each other. Why it will fall into nucleus or why it will not go to electron? Because of here equal amount of centrifugal force will be applied. So here equal amount of centrifugal force will be applied. Here Coulombic force is applied. So that's why electrons are revolve around the nucleus. Here these electrons are called bounded electrons. So it will be bounded. Okay, so these electrons are called bounded electrons. So here maximum number of electrons in nth orbit. How can we find out? Is 2n square by 2n square. So here n is orbital number. Suppose n is 1. Suppose n is 1. So in 1th orbit, how many electrons are there? 1 square into 2. So 2 electrons are there. So like that, how nth orbit gives the number of electrons. So electron will not affect the nucleus. So here electrons revolve around the nucleus. Like this, electrons are there, bounded electrons are there. We want to electron will become a free electron. Some energy is required. You want to become a free electron, some energy is required. So that energy is called ionization potential. When electron will become free electron, some energy is required. That energy is called ionization potential. So it is nothing but it is the amount of energy required for the valency electron to become free electron is called ionization potential. So how much energy is required to become a free electron for free electron? So the formula is the energy required to become a free electron. The formula is minus 13.6 by n square electron volts. So here 1 electron volt is equal to how much? 1 electron volt is equal to 1.6 into 10 power 19. So in this, radius of an atom is given by radius of an atom is given is equal to radius of an atom is equal to 0.529 angstroms. 529 angstroms. So 1 angstrom is equal to 10 power minus 8 centimeters or 10 power minus 10 meters. Suppose we want to find out for hydrogen atom. So how much energy is required to become a free electron for hydrogen atom? So for hydrogen atom, how much energy is required? The energy required for hydrogen atom is minus 13.6 by hydrogen atomic number is 1 square electron volts is equal to minus 13.6 electron volts is required to become a free electron. To become a free electron. So here in this we have to be observed in this bounded electron, this electron will be bounded or it will be free electron or it will be free electron. Only these two things will be happen here. It will not stay middle. So this is called forbidden gap. Forbidden gap means prohibited, not allowed. So here the electron will not stay between the valency band and conduction band. It will be stay in valency band or in conduction band. Okay, so electrons stay bounded electron or free electron, not stay in between. So it is called forbidden gap. So silicon atom forbidden gap at room temperature is silicon atom forbidden gap at room temperature is 1.1 electron volts. So germanium atom forbidden gap is 0.72 electron volts. 0.72 electron volts. So here we know very well conductors, semiconductors, insulators. So conductors, semiconductors, insulators. Before going to discussion of energy band diagrams, so here the gap, energy gap between valency band and conduction band in semiconductor is how much? 1 electron volts. So the energy gap between valency band and conduction band in semiconductors is 1 electron volts. So here valency electrons. What is the definition of valency electrons? Electrons in the outermost orbit of an atom are called valency electrons. The number of valency electrons present in an atom varies from atom to atom. If the electrons in the outermost orbit are 8, then the atom is said to be stable. We know very well. What are the examples for that? Helium, neon, etc. Okay, so various substances which are available in universe are classified into three groups depending upon the valency electrons. What are those? Conductors, conductors, semiconductors, insulators. Conductors, semiconductors, insulators. So what are the examples for conductors? So which one we treated as a conductors? So the examples are conductors are copper, aluminum, gold. Copper, aluminum, gold, etc. What are the examples of semiconductors? Germanium and silicon. What are the examples for insulators? Paper, mica, glass, etc. What about temperature coefficient of resistance? So temperature coefficient of resistance is positive temperature coefficient of resistance. How can you say it is a positive temperature coefficient of resistance? We know very well the formula of RT is equal to R naught into 1 plus alpha T. So here when temperature increases, when temperature increases, so what happened? Resistance also increases. When resistance increases, what happened? Current will be decreases. So that's why it is a positive temperature coefficient of resistance. Positive temperature coefficient of resistance. So come to the semiconductors and insulators. Both are negative temperature coefficient of resistance. Both are negative temperature coefficient of resistance. It will be denoted as alpha. So because of that, the formula is RT is equal to R naught into 1 minus alpha T. So here what happened? When temperature increases, resistance decreases, current increases. So it is a negative temperature coefficient of resistance. This is a negative temperature coefficient of resistance. So here, which one you have to be say? Semiconductors. Fourth group of elements. Fourth group of elements is called semiconductors. So that means valency. In valency, 4 electrons are there. Those will be called as a fourth group of elements. So electrons in the outermost orbit of an atom are called valency electrons. In semiconductors, what type of elements are there? So we have to be observed in fourth group of elements, carbon, atomic number is 6. So carbon, silicon, germanium, tin, lead. So here we have to be observed carbon, silicon, germanium, tin, lead. So when we draw the valency of these, so depending upon the configuration, so carbon will be 6. So it is in the nearer. So remaining are farmost nucleus. So tin, lead are very far away the nucleus. So it is very easy to become a free electron. It is very easy to become a free electron. So that's why tin and lead have the conductor properties. Conductor properties. Germanium and silicon as semiconductors. Carbon acts as a insulator. Carbon acts as a insulator. So in this carbon. So here in this carbon, it required the energy gap is 6 electron volts. It acts as a insulator. It required 6 electron volts. So silicon, germanium required so 1.1 electron volts. This will be required 0.72 electron volts. Tin and lead required zero point 0.1 electron volts. It will be very less. It will be become a free electron. Very less energy is required. So energy band diagrams of conductors, semiconductors, insulators. The conductor's energy band diagram is, it is a overlap each other. Overlap each other. So here in this energy band diagram, we know very well this is the energy band diagram. That means a group of closely spaced energy levels in an atom is called energy band. Conduction band. So this is the conduction band. This one is valency band. What it is called conduction band is the upper energy band with empty energy state is called the conduction band. So this is valency band. Valency band is the lower energy band which is filled with valency electrons is called valency band. In semiconductors, so it required the forbidden gap is 1 electron volts. So this is conduction band. So this one is valency band. So what is forbidden gap? The separation between valency band and conduction band is called forbidden gap. So this is measured with electron volts. So here in conductors, it consisting less than 4 electrons. So in conductors, valency electrons are loosely coupled to the nucleus. So here there is no forbidden gap. Conduction band and valence band overlap each other. These two are overlap each other. All metals are the examples of conductors. We know very well. Previous we have to be discussed. Okay. So conductors are positive temperature coefficient of resistance. What about insulators? So in this insulators, the energy band diagram is, this is conduction band, valency band. It consisting 6 electron volts. 6 electron volts. So here, because of 6 electron volts means here the in a valency band, electrons are tightly coupled. Okay, in this valency electrons are tightly coupled to the nucleus, hence required large external energy to become a free electron. So that is 6 electron volts. So here in case of insulator, forbidden energy band is very wide. So it will be, it cannot be jump valency band to conduction band because of 6 electron volts. Some more energy is required. Here very high energy is required. So insulators have negative temperature coefficient of resistance. So we know very well examples of insulators, diamond, wood, glass, etc. So here valency should be 7 and more. So in semiconductors, we know very well, in semiconductors, these have 4 electrons in the outermost orbit. Energy gap of semiconductor between that insulators and conductors. So that is 1 electron volt. So what are the examples of semiconductors? Germanium and silicon. So in this germanium and silicon, which one most preferable one? So silicon is most preferable, even though even though we will be call it as a silicon controlled rectifier, not for germanium controlled rectifier, because of silicon is very easy to affiniated with oxygen and it has high temperature withstanding capacity. So here the energy gap required for silicon is 1.21 electron volts at 0 degrees Kelvin, 1.1 electron volts at 300 degrees Kelvin. So what about germanium? So germanium required 0.782 electron volts at 0 degrees Kelvin, 0.72 electron volts at 300 degrees Kelvin. So here in semiconductors, carbon. So this carbon will be accessed in different ways. So it will be in the form of available in diamond shape. It acts as an insulator. It will be available in the form of diamond shape. Carbon acts as a insulator. Amorphous powder. It will be available in the form of amorphous powder form. It acts as a semiconductors. When it will be available in the graphite, it acts as a conductors. It acts as a conductors. So now among these three, which one is more popular? Semiconductors are more popular. So in these semiconductors, we have to be discussed now. In semiconductors, elaborately we have to be discussed semiconductors. In semiconductors, we know the energy gap between semiconductors is, so this is the conduction band. So this one is valency band. So the energy gap, forbidden gap is 1 electron volts. So when at 0 degrees Kelvin, so that means the valency band is completely bounded with electron. We don't give any type of energy. So at that time what happen? So nothing will be happen. There is no free electrons will be available in conduction band. So that means at 0 degrees Kelvin, the semiconductors acts as a insulator. At 0 degrees Kelvin, semiconductor acts as a insulator. When you have to be give some energy, what happen? This electron will jump from here to here. So this, when it will come to conduction band, that electron will call it as a free electron. Here what happen? Hole will be created. So here also, when you will be given to some energy, this electron will jump from valence band to conduction and hole will be created. So I will be write it as a in different color. Hole will be created. So here, when electron will jump from valency band to conduction band, hole will be created. So some energy is required to jump electron from valency band to conduction. When you have to give that energy in the form of temperature or light, what happen? So bonds are break and jump valency band to conduction band, hole created. So what is hole? What is the definition of hole? Absence of electron is called hole. Absence of electron is called hole. So here, after some time, when it will be jump from valency band to conduction band, electron will travel sometime here. After some time, it will be fall into the valency band. So that is called recombination. So here, in after recombination, so how can you say the life mean lifetime period. Mean lifetime period of electron. So electron generation to recombination time period is called mean lifetime period. Just like our life, we have to be birth and death. In between some life will be happen. So same way electron will generate and recombination. In between sometime it will be travel. After that it will be recombined. So that is called mean lifetime period. So depending upon material, so it will be heat produced or sometimes it will be light produced. So when you have to be used the semiconductor material is germanium and silicon, it will be produced heat. When you have to be used the that material is gallium arsenide phosphide, like that light will be produced. So those are the LEDs. Light will be produced. Okay. So here we have to be observed in semiconductors. The valency electron is 4. Valency electron is 4. It will be bounded with another electron. See the diagram. This is only structure of bounded electron. So this will be bounded. When you don't give any type of energy, what happen? It will not move here. When you have to be apply some energy, so what happen? It will become a free electron. So at that time hole will be created. So here when it become a free electron, here hole will be created. When bound electron become free electron, then only current will flow. When bound electron become free electron, then only current will flow. So in intrinsic semiconductors, so here hole will be created. So that is absence of electron. So at 0 degrees Kelvin, nothing will be happen. When we have to be apply some energy, so at that time it will become free electron, current will be flow. So in intrinsic semiconductor, here the question is in intrinsic semiconductor, current is due to A, electrons only, B, holes only, C, both electrons and holes, D, 0. Here the answer is both electrons and holes. So here we have to be observed when this consisting electrons and holes it will be connected to a through a wire. So what happen generally? So electrons will attract to here, holes will be attracted to here. Like that we have to say. But whole current means what? Here whole current means hole should not move. Electrons move and reach to hole, like that come out, that is whole current. That means suppose in our college in bench have three members of students. So three members of students will be, we will be treated as a electrons. So one member will be shifted to another place. What happen? Some other member will come to that place. So when vacant will be happen, that is called hole. Bench will not move. So here bench will not move. So in this bench, three members are there. So this person will go outside. So what happened here? Hole will be created. This hole will not move. Some other person will come and sit. So that is electron. So because of electron movement, hole current will be generated, not holes are moved. So that is most important point here. So hole is a absence of electron. Hole should not move. Here current due to in conductor, current due to only electrons. So in extrinsic semiconductor, in name itself, it has extrinsic. So here germanium and silicon, pure semiconductors, practically the current will not sufficient. So we added some doping, impurity added to material. So 1 in 10 power 7 atoms we will be added, conductivity increases 1000 times approximately. So when doping concentration increases, conductivity increases. So adding of impurity to a intrinsic semiconductor, that is doping the material is formed, is called extrinsic semiconductor. So adding impurities to a intrinsic semiconductor, that is doping the material is formed, that material is called extrinsic semiconductor. So in extrinsic semiconductor, two types are there: N type, P type. N type, P type. Okay, so how can you say this one is N type and this one is P type? Means by doping with fifth group of elements, by doping with fifth group of elements is called N-type material. So what are those fifth group of elements? Phosphorus, arsenic, antimony, bismuth. So what type of material is called as P-type semiconductor material? By doping with third group of elements is called P-type. So what are the examples for? So here third group of elements. What are the examples? Boron, aluminium, gallium, indium. Here in this N-type semiconductor material, energy band is, so we know semiconductors, conduction band, valency band. Actually, 1 electron volts, forbidden gap is 1 electron volts. For germanium 1.1 electron volts, silicon 0.72 electron volts. So already we have to see the structure of silicon. It is the valence is 4. When fifth group of elements you have to be taken. So that means what? Here 5 valency electrons are there. So in this we have to be observed what happened. So each and everything will be bonded. So what we have to be observed here, only this electron will be there. So here the energy is required is very less. This will be become a free electron. Energy required is very less. So that is 0.05 electron volts. It is loosely coupled. So remaining all are tightly coupled. So this is loosely coupled. So remaining all are tightly coupled. The energy required is more. So this electron will required to become a free electron. Suppose it is a germanium. Suppose it is a germanium or silicon. 1.1 electron volts, 0.72 electron volts is required because it is bounded electron. So this is free electron. So that's why this electron required very less energy to become free electron. So because of that, so here because of that, so the energy gap is very less. So this one is 0.05 electron volts. So it is very easily in valency band. When you give some energy here to here valency band to conduction band, some electrons will jump, and at the same time here also when you have to be doped with fifth group of elements, here some electrons are jump from conduction band, it will become a free electron. So the current will flow. Because of that, majority carriers in n type is, because of that majority carriers in n type is electrons. Minority carriers are holes. So same way, in third group of elements, suppose we have to be added, same diagram will be modified here. So before it is n type, now it is p type. So instead of phosphorus, I will be taken as boron. So what happened? So here outermost is third group because of 3 electrons. Here already some vacancy is there. So it is ready to accept the electron. Before it will ready to give the electron. So that is called donor. This is called acceptor. So here what happened? So it is very easy to jump. So because of that, in p type majority carriers are holes. Majority carriers are holes. Minority carriers are electrons. Minority carriers are electrons. So now the charge of n-type material. The charge of n-type material is, generally everybody says it is a negative charge, like that. So not that answer. The charge of n-type material is electrically neutral because of, so fifth group of elements is 5 electrons. Silicon atom, here electron move to free electron, positive ion will be created. So here previous we have to be observed what is there. So here some electron is there. So this is phosphorus. Here some electron is there. So it will be it will, when it will become a free electron, here hole will not create. So here some positive ion will be created. So that's why, so it is electrically neutral. This charge carriers called Nd plus donor ion. So this charge carriers is called donor ion. Donor ion. Okay. So charge of n-type material. Charge of n-type material is electrically neutral. N-type material is electrically neutral. Charge of n-type material is electrically neutral. Same way in p-type. So it is a acceptor ion. It will become a acceptor ion. Minus. Acceptor ion. So these are the donors. These are the acceptors. These are the acceptors. So in this, n-type material is popular than p-type. Among these, so n-type will be formed adding a fifth group of elements. So compared to that p-type, n-type materials are popular. Why? Because conductivity is due to electrons. Electrons have higher mobility. So that's why the n-type material is popular than p-type. So next one, mass action law. This is very important. Mass action law. In case of extrinsic semiconductor, number of electrons and holes product is called Ni square. So Ni is the intrinsic concentration. So Ni is intrinsic concentration. So the formula of Ni is equal to A naught T cube e power minus Z naught by Kt. Here A naught is a material constant. So this is the material constant. This is temperature e power energy gap at 0 degrees Kelvin. So this is energy gap at 0 degrees Kelvin, Boltzmann's constant, temperature. So Boltzmann's constant to temperature. So here Ni depends material constant and temperature. Ni depends material constant and temperature. So when we have to be taken n-type material, we increase the doping concentration. What happen? Number of electrons increases. Temperature maintained constant. Minority carriers decreases. Finally, product is constant. So mass action law, what it states is at thermal equilibrium, doping increases. At thermal equilibrium, doping increases. What happened? Majority carrier concentration increases. Majority carrier concentration increases. Minority carrier concentration decreases. Minority carrier concentration decreases. So finally, the product is constant. Finally, the product is constant. So in intrinsic semiconductor, N is equal to P is equal to Ni. So now we have to be discussed drift current and diffusion current. Before going to drift current and diffusion current, we must know the what is electrical potential and electrical intensity. So we have to be discuss next topic is drift current and diffusion current. Before going to drift current and diffusion current, we must know the definitions for electrical potential. V, nothing but work done. Electrical intensity, denoted by E. So we take some field. Unit charge, energy required to bring this unit charge from a infinite infinite distance, that corresponding energy level is called electrical potential. What is electrical potential? Energy required to bring this unit charge from a infinite distance, that corresponding energy level is called electrical potential. What is electrical intensity? Force required to bring, some force required to bring unit charge is called electrical intensity. So finally it is a, what is the difference of this? This is work done. So this is force. So what terminology we have to be used? Force and work done. Okay. So here the formula for work done is equal to force into displacement. Force into displacement. Displacement or distance. So W is equal to F into D. From this, potential V, potential V is electrical intensity. What letter? It is denoted E into D. So small voltage of dV is equal to electrical intensity into small distance of x. So what is the electrical intensity? Electrical intensity is equal to dV by dx. So volts by distance. Volts by distance. So that is volt per centimeter. Sometimes electrical intensity is equal to negative potential gradient. Sometimes electrical intensity is equal to negative potential gradient. So minus dV by dx. So now we have to be discussed diffusion current, drift current. So diffusion current. What is diffusion current? We have N-type material. We have N-type material. So number of electrons are there. Doping concentration is high. So what happened? Electrons move from one place to another place without any electric field. So electrons move one place to another place without any electric field. is called diffusion current. So here, for example, some sponge is there. You have dropped one ink point. So first of all, it will be in one place. After that, it will be spread all over sponge. So otherwise, one more example. So in glass, some water is there. We have dropped one ink point. So what happened? First, it will be go slowly and spread all those things. So like that. So what happened? The electrons move one place to another place without any electric field is called diffusion current. So that means without any electric field, the movement of charge transportation, charge carriers, higher concentration to lower concentration. The type of current is called diffusion current. So it will be what happened here. So it will be move higher concentration to lower concentration. So that type of current is called diffusion current. So this diffusion current is independent of electric field. So this is independent of electric field. It depends on concentration gradient. It depends on concentration gradient. So next one, drift current. Next one is drift current. So when we taken one n type of material, have to be apply some. So here electrical intensity E. So this is electrical intensity E. N-type material, positive charge, negative charge. Due to electrical intensity, force attract the electrons, due to that current will take place. So here Vd is proportional to electrical intensity. So this is drift velocity. Vd is proportional to electrical intensity. So Vd is equal to mu E. So what is mu? Mobility. Mu is a mobility. Mu is a mobility. So here mu is a constant. So for that, we want to find out that mu is equal to Vd by E. So this is what? Drift velocity. What is the units for this drift velocity? Meter per second or centimeter per second. So what is this? Drift velocity. What are the units for this? Meter per second or centimeter per second. So this electrical intensity, volt per meter. Volt per meter. So what is the units for mobility? Meter square by volt second or centimeter square by volt second. So these are the units. Mobility depends on type of semiconductor or nature of the material. So mobility depends on temperature. So this mobility depends on temperature and electrical intensity. So this will be depends on type of semiconductor or nature of the material. Or nature of the material. So next one, charge density in semiconductor. Charge density in semiconductor. So We want to calculate minority carriers. For example, N type. For example, N type. What are the majority carriers? Electrons. For majority carriers in N type is electrons. Minority carriers, holes. We know very well. So, majority carriers means positive ions. Electrons means positive ions. So, that indicated Nd plus. In previous, we have to be discussed that. Same way, in P type, majority carriers are holes. Minority carriers are electrons. So, in this, denoted Na minus. It will be denoted Na minus. So electrical neutrality. How can you say electrical neutrality? Positive charge is equal to negative charge. Positive charge is equal to negative charge. Means holes plus donor ions Nd plus is equal to electrons plus acceptor ions Na minus. So here electrical neutrality. How can you say electrical neutrality is holes plus donor ions is equal to electrons plus acceptor ions. So calculate minority concentration. N into P is equal to Ni square. In N type, we know very well donor ion Nd is equal to N. Initially assume holes approximately 0. So N type Nn Pn. So this is electrons and holes in N type is equal to Ni square. So that is what here denoted. N means Nd. So we replace that Nd Pn is equal to Ni square. When we want to find out that minority carriers is equal to Ni square by Nd. Ni square by Nd. Same way in P type. So Np is equal to Ni square by Pp. So that is nothing but Ni square by Na. So in P type it is acceptor. So that's why both sides Ni square is common. Only it is N type. We have to be denoted Nd. Nd. It is a P type acceptor. So donor acceptor. So the formula is very important. Pn is equal to, so when minority carrier concentration calculated, Pn is equal to Ni square by Nd. P type Ni square by Na. So next one, drift current density. Drift current density. Drift current density. Current density. What is the formula for I? I is equal to Q by T. Means charge by time. So that is also, we write it as a E by T. That is also write it as a E by T. Suppose volume of these electrons are there. Current is equal to NQ by T. Number of electrons by T. So what is the formula for J? J is equal to I by A. So that is I means NQ by T. I means NQ by T. So that substitute what we get? NQ by AT. We know very well VD is equal to L by T. T is equal to L by VD. So substitute that one. What you get? What you get? NQ VD by A into L. So this is electron per unit value. Electron per unit value. So that's why J is equal to NQVD. Electron per unit value. So this NQ is charge density. This NQ is charge density. Okay. What about J? At that time, J is equal to NQ VD, drift velocity. We know very well VD is equal to mu E. VD is equal to mu E. When we substitute VD is equal to mu E, what happened? Instead of this, mu E. This NQ mu is called conductivity. Conductivity. That is denoted J is equal to sigma E. That is denoted J is equal to sigma E. So here J is a current density. J is a current density. This is conductivity. So this is Ohm's law. It related to Ohm's law in vector analysis. This is Ohm's law in vector analysis. So it will be in N type is NQ mu N. So it is a P type PQ mu P. So diffusion current diffusion current Jn is equal to Q mu n dn by dx. So with respect to distance, the concentration what happened? Decreases. So current density due to electrons. Current density due to electrons is Q mu n dn by dx. So what happened? Electron charge minus with respect to distance the concentration is decreases, so that is minus. So minus minus will get a plus Q. So in J current density due to holes is equal to current density due to holes is equal to minus Q mu P dP by dx. Minus Q mu P dP by dx. So diffusion current density due to electrons is Q mu n dn by dx. Current density due to holes is minus Q mu P dP by dx. So here in mass action law, the product of total free positive charges and free negative charges in the semiconductor is equal to the square of intrinsic concentration. This is called mass action law. So Np is equal to Ni square. So N is electron density, P is hole density, Ni is intrinsic concentration. Okay, so this is drift current, diffusion current. So finally, in semiconductor currents are two types of currents, drift current, diffusion current. So drift current is, it is the current which flows when external battery is connected. It is called a potential gradient. So diffusion current is, it is the migration of charge carrier from higher concentration to lower concentration. Migration of charge carrier from higher concentration to lower concentration. So next one, Einstein relationship. You know very well. Einstein relationship. Einstein gave a relationship of both diffusion constant and mobility which are dependent. So dP by mu p is equal to dN by mu n, that is nothing but Vt. So volt equivalent of temperature. V is volt equivalent of temperature. So that Vt is equal to Kt by Q, that is equal to T by 11,600. Hence at room temperature, that is 300 degrees Kelvin, what is the Vt value? So Vt is equal to 300 by 11,600. So that is 25.86 millivolts, nothing but 26 millivolts. So here K is a Boltzmann's constant. At room temperature, Vt is 26 millivolts. Okay.